In London, in the 1830s, inventor Charles Babbage was designing his magnum opus. Working by the light of an oil lamp, he sketched out his plans for the Analytical engine. He drew a hulking mechanism with clicking brass cogs and cams spun by a steam engine and orchestrated by the same punch cards that ran mechanical looms. In an era when the electric telegraph was a novelty, Babbage had invented history's first fully universal programmable computer. It's a glimpse of a steampunk future that never was. The design remains unbuilt to this day. But it did catch the attention of Babbage's friend, Ada Byron Lovelace. Lovelace had admired Babbage's last invention, a simpler mechanical calculator. So she decided to translate notes from one of Babbage's lectures about the Analytical engine, and added pages and pages of her own comments. These include the very first published computer program, which would calculate Bernoulli numbers. Though the program did have one small error. Programmers can relate. On the very same page, Lovelace brought up a question that would hound engineers and philosophers for centuries to come. Can computers come up with their own original ideas? Lovelace herself had a pretty clear stance that they couldn't, or at least Babbage's computer couldn't. The Analytical engine has no pretensions whatsoever to originate anything, she wrote. It can do whatever we know how to order it to perform. Over the entire history of computing, as computers have gotten better and more sophisticated, many others would try to tackle the same question. And with today's AI, it's become more relevant than ever. What makes this question so tough is that it's not clear what counts as a new idea, and it's easy for people to move the goalposts. There's no obvious bright line between unoriginal and original thoughts. To some extent, every idea we consider new is built on what came before. It's a matter of degree. In 1951, an early computer at Cambridge University found the first known 79-digit prime number, but that was just following simple mathematical instructions at high speed. It's a new fact, sure, but not an original idea. What about in 1997, when the computer Deep Blue beat world chess champion Garry Kasparov? Deep Blue certainly had to come up with some original chess play, since no one had previously played against the exact moves that Kasparov chose to make. But Deep Blue was just searching through the possible moves, mostly by brute force, and the methods that Deep Blue used to ignore bad moves had to be programmed in by hand. So maybe the specific moves were decided by Deep Blue, but the overall method for finding them was up to the human programmers. The same might be said of tools like genetic algorithms, which can solve problems by iterating on designs and improving them bit by bit. Genetic algorithms have designed very efficient spacecraft antennae. They can even design computer hardware in ways that are quite different from conventional human methods, by exploiting messy physical side effects that humans wouldn't consider. Still, even though the output of genetic algorithms might be novel, it's easy to dismiss them as still blindly following human instructions, with a little bit of randomness thrown in. So what about AIs based on neural networks and machine learning? You can open up your favorite chat assistant, and it can hold a conversation or write a computer program for you. It definitely seems to have some amount of creativity, at least compared to Deep Blue. But again, original ideas are hard to define. People still haven't firmly planted the goalposts. Some critics dismiss modern AIs as stochastic parrots, a term introduced by Emily Bender in a 2021 paper with 3 of her colleagues. The paper argued, among other points, that LLMs didn't actually understand the meanings of the words they strung together, no matter how coherent the resulting sentences sound. We have a lot of evidence that AIs understand what they're saying, in the sense that they encode information in their neural nets beyond just statistical relationships between words. One famous interpretability study from early 2023 trained a neural network just on written records of legal moves in the board game Othello. Probing its internal activity, researchers found that it was tracking something extremely close to the true board state at every move, so it didn't just memorize which words usually go together. In a more recent paper, from May 2025, interpretability researchers at Anthropic tried to trace the thoughts of Claude 3.5 Haiku. For one experiment, they prompted Claude with, quote, "Fact, the capital of the state containing Dallas is," end quote, and Claude correctly responded, "Austin." Then, using a tool called attribution graphs, the researchers uncovered that Claude hadn't just memorized that complete fact. Instead, it was reasoning in multiple steps, that Dallas is in Texas, and that Texas's capital is Austin, and it was able to combine those facts to find the right answer. There's also a phenomenon called grokking, where a neural network that has already memorized its training data will, after much more training, start to generalize well to unseen examples of the same task. Interpretability studies have found that, over time, the network gradually shifts from relying on heuristics and memorization to implementing a simpler, more structured rule that captures the underlying patterns in the data. These examples demonstrate a deeper point. Even if an AI's only training objective was predicting data based on patterns, it could still learn facts about the world and how to reason with them. In principle, if your goal is to predict future information, you'd do better if you understood the world. Predicting where a satellite will go is easier if you understand the laws of physics, for example. Coming up with original ideas can help make better predictions too, like how when Einstein developed general relativity, he was able to better predict the orbit of Mercury. To be clear, even if today's AIs can extrapolate facts and laws about the world just by learning to predict the next token, they don't necessarily generalize in the best way. A paper from 2025 found that a small transformer trained to predict planet trajectories performed badly when fine-tuned for other tasks that required understanding of Newtonian physics, like predicting gravitational forces. Now, this transformer model was at least 1,000 times smaller than something like ChatGPT is today. Perhaps this smaller AI wasn't grokking the problem and really was just predicting the next observation. That said, today's AIs aren't just trained to predict the next word. To simplify a bit, they're usually trained in two segments. The first is pre-training, where they learn to predict the next token of internet text. The second phase is post-training, which includes reinforcement learning. During this phase, AIs learn to do much more. Let's look at pre-training and reinforcement learning in more detail. Today's AIs can deal with images, videos, and speech, not only text. But let's just consider text right now. During pre-training, an LLM learns patterns in written language and the structure of the world that language represents. It churns through tons of content, and the billions or trillions of parameters in its neural network get tweaked until it can effectively predict what comes next after a piece of text. What the AI learns during this phase acts as background knowledge it can use to learn better during the next phase. In reinforcement learning, the LLM is further trained so that it gives responses in pursuit of different objectives. These could be acting like a helpful, honest, and harmless assistant, writing working computer code on request, or solving difficult math problems. In short, the AI isn't incentivized to exclusively predict human text anymore. It needs to learn to do a variety of other things, including solving actual problems that require planning, tool use, and reasoning. Might this training imbue an LLM with something akin to creativity? Well, being able to come up with your own original ideas would certainly improve performance at these kinds of tasks. Often, the feedback for this process comes from human observers, as it does from reinforcement learning from human feedback, or RLHF. Other AIs, even weaker ones, can also give feedback, since it's generally easier to verify a proposed answer than to generate a good one from scratch. Like how it's easier to tell if a YouTube video is any good than it is to create a good video yourself. Sometimes, feedback can even be a simple automated test, like just running the code written by the AI in training and seeing if it works correctly. Any of these options can push an AI toward thinking creatively if we're asking it to solve complex problems. Consider Alethea, a system designed to solve open problems in mathematics, described in a paper in February 2026. Alethea works using 3 subsystems, each using Google's Gemini and full access to the internet. One system generates candidate solutions, the second searches for errors independently, and the third tries to fix any errors that crop up. If the errors can't be fixed easily, the problem goes back to the generator to try again. Google's researchers gave Alethea many different open problems in mathematics. Eventually, the system found a new result worth publishing by applying tools from one subfield of mathematics to a problem in a different one, in a novel way. The researchers turned it into a paper, Eigenweights for Arithmetic Hirzebruch Proportionality, and submitted it for publication. And Alethea isn't the only AI system working on research challenges. Google's AlphaEvolve works as a meta-level search algorithm, with a program that searches for the best solutions to quantifiable problems, and language models that suggest and test ways to make that program more effective. AlphaEvolve has also found some publishable results. OpenAI's models are also helping with new research. A team of human physicists used GPT 5.2 to help find new results in theoretical particle physics, showing that when particles called gluons decay in a particular restricted way, they can produce certain combinations of other gluons that are usually impossible. Once the physicists had worked out several specific cases by hand, GPT 5.2 suggested a more general formula, and another OpenAI model proved it was accurate. And all this is just the start. There are probably even more impressive results on the way, even by the time you're watching this. So we have evidence that AI understands its words on some level, and AI systems are starting to find new research results. These ideas certainly seem at least a little original, but are they original enough to count? Maybe you're still waiting to see an AI that can solve its own interesting research questions, rather than straightforwardly answering someone else's. Well, what matters here is not if today's AI systems are coming up with ideas as original and as useful as the best human ideas. It's that computer programs have been steadily improving, coming up with ideas that are increasingly more original and more useful over time. Alethea's new results are a step above Deep Blue's chess strategies, which are in turn a step above finding new prime numbers. Looking ahead, experts are expecting AI to get even better at tasks that require creative thinking. Epoch AI tracks the progress of AI in many areas, including with their popular Frontier Math benchmark, which tests AIs on advanced math problems. In January 2026, Epoch released a new benchmark, Frontier Math Open Problems, a collection of 14 unsolved research-level problems, ranging from moderately interesting questions to ones where a solution would be a true breakthrough. It's just one more step in the path of machines getting more creative. Sure, progress has mostly been gradual, but it all adds up. Imagine how Babbage and Lovelace would react to modern LLMs. Most people can't even distinguish the best LLMs from humans in a 5-minute text conversation, just one of the latest milestones in computers passing the Turing test. It's natural for people to want to move the goalposts. Sure, AI can write a novel, but can it write a bestseller? But rather than comparing AI to a standard that keeps moving just out of reach, look at the trend line. You'll get a much better sense of where we're going if you compare AI's current capabilities to what they could do a few years ago. And this isn't a new conversation. Turing argued against Lovelace in the same paper that introduced his imitation game test, and we certainly won't be the last word on this subject either. The discussion will certainly shift as AI improves. But however you might define it, AI is already surprisingly original, and thinking in absolutes won't help understand it. If you'd like to learn more about AI and get involved with the effort of making it safe, AIsafety.com is a hub for navigating the AI existential safety ecosystem with many resources, listing things like in-person and online groups, upcoming events and training programs, funding opportunities, self-study courses, a map of the field, and much more. It also has a curated video playlist on AI safety, featuring many of our videos.